Alright, so electric fields. Now, what are they? So we also call them E-fields because sometimes we don't feel like saying the word electric over and over again. And we have electric charges that are creating these electric fields. At least that's just how we're going to view it now. It might not entirely be the case later on, but for now that's what we're going to say. Now these are vector fields, meaning that they have a magnitude and a direction. And their units are in newtons per coulomb. Let's see what that means. So here we have charge Q1 and we have Q prime. Now Q prime does not have a charge, it is a point. But usually when we're calculating the force, we need to know the charges of both of these points, right? Well, here, the equation for the electric field is the force divided by Q prime. And when we divide this equation for our electric force divided by Q prime, the Q primes cancel out, and all we're left with is this equation, which is K Q1 over R squared. So whatever Q prime is, it doesn't matter, we don't care about it because we are trying to find out the effect Q1 has on any point in space. So we have Q1 here and it has a charge of 10 microcoulombs. Q prime is just a point, no charge, and they are separated by 2 centimeters. We want to find the electric field caused by Q1. The equation, as we just derived, is E is equal to KQ over R squared. K is Coulomb's constant, which is 9 times 10 to the 9 Newton meters squared over Coulomb squared, times our charge, which is 10 microcoulombs, so changing that to coulombs because we need our SI units, is 10 times 10 to the minus 6 coulombs. Divide all of this by 2 centimeters, which is 0.02 meters squared. And the electric field obtained is 2.25 times 10 to the minus 10 newtons per coulombs. So what does this mean? Well, it means that if we have a charge here that's just floating around in space, it is going to affect all the different points around it. So here we have a charge, which is Q. Then let's say we have Q prime down here. If we were to calculate it using the equation example we just did, we would be able to find that it has a magnitude and that it has a direction because it's a vector. And the direction it's going is perpendicular to our point. So here is a straight line from the center of the point all the way up here. This is telling us that this charge here is affecting this point in space way down here. And it's saying that it's affecting this point in space down here. But see, when a point is closer to the charge, it has a longer line because it has a larger magnitude. If you're not too sure of why that is, try plugging in small values for the distance and large values for the distance in the previous equation, and you'll see that when the distance is smaller, the electric field is going to be bigger. So now, how does that translate into this? Well, here at the center, we have our charge. And this charge is positive. How do we know it's positive? Well, we see that the electric field is pointing away from it, and that's what happens when a charge is positive. Now, at this point right here, we see that it's pointing away, and it's pointing away everywhere. And this is what we mean by an electric field, because this little point here is having an effect on the region all around it. This will be pretty useful coming up, and the next thing we're going to look at is field lines.